Hey everyone, we are the team Memory Maestros. I am Hitesh Kumar and my teammate is Vardhan. We are a team of two and we worked on the project Memory Cache Hierarchy of Graph Analytics. So here is the flow of our presentation. First, we will talk about objectives of the project, like what we have to implement in the project. Then secondly, we will talk about how we planned the project and how we go through it. There are various problems we face during the implementation, which we will say later, and also like how we try to solve them is also covered. Then in last, we will talk about the results we got using the ChampSim simulator. Now moving toward the objective part. The first objective is to improve the memory performance on the workload, which are based on the graph. And the second goal is to make it faster to access the cache by organizing it better. This helps reduce the delay in getting faster information from the cache. So how we are able to do this? We are able to do this with the implementation of the inclusive cache memory system. Now in planning, we first find the research papers which pertain somewhat to graph processing. Then we set up our tools for the system of the purpose and we use ChampSim simulator for this as required. Now in the ChampSim, we implemented the inclusive memory hierarchy. In the end, we looked at some graph to better understand how the CPU was being used in different scenarios. And we combined this information with data from ChampSim to compare the results. Now getting started, we first cloned the original ChampSim directory which is provided into our private repository and then we read a lot of research papers. I have also given the links of the research papers also in the slides. And in one of the research papers we read, there was about the properties of inclusive cache structures and how they can be implemented in the ChampSim is given. So we try to implement that in our ChampSim simulator. Now moving forward, I will hand over to Hers. He will continue forward.
So now, as Hitesh described, I'll be talking about the hurdles we faced along the way. So we know that life isn't a bed of roses, and this project was no different. Given that we also had to complete in a lot of less time. So I'll be describing the problems. The first problem was the research papers. All of them, almost all of them, they assumed that we had some special processing data set which could be geared towards graph data structures. For instance, some of the replacement policies such as pop and pin, they used the frequency at which the graph address was used, which can indeed be stored in a regular cache, but they also use some other metrics such as the size of the graph and the latest used distances, which are only possible when we change the instruction set. As far as I know, that is not really feasible with ChampSim. It uses a fixed ISA, and so that route we couldn't go down. So we are really limited as to what we could do. One thing was implementing some basic replacement policies, but we could not find papers on that. So what we are left is make our cache organization system inclusive or exclusive and try to experiment with that. But then again, ChampSim as a tool is more suited towards testing out new prefetchers or branch predictors or replacement policies. It is not really geared towards changing the cache organization. Usually cache organization in ChampSim is non-inclusive. Changing that to inclusive requires a lot of work because first things first, we can directly change it. We need to make functions to ensure that properties such as inclusiveness are always followed. Finally, once all of this had been crossed and we had successfully implemented inclusive cache and tested it, we noticed that in some cases latency was missing in the report. For instance, while testing out the traces of page rank, we noticed that the load in L1 cache instruction latency was missing in every case. So we had to filter that data out, and as a result, that rendered page rank data useless, because this connects with my next point. What we observed after running this test is that using an inclusive cache results in a lot of optimization for reducing the latency of L1 instruction cache, and as expected of inclusive cache, it also reduces the write back misses to zero. Something which is present in the higher level cache will always be present in the lower level cache as well. So these are the two things, and there were no significant other changes in other data related caches like L1D and L2C and LLC. Not much changes there. What we believe though is that using an exclusive cache could help reduce the latency for that part. There is a reasoning behind that, being instructions are almost always fetched in a sequential manner. So once they are loaded in L3, they will always be propagated to L2 and L1, and that greatly reduces the latency of instructions. But for graph related workloads, that might not be the case. Data might be used randomly all over the place. So that's why we didn't see a lot of improvement while making an inclusive cache. That is because the data was not always correct. We don't have a good prefetcher to go along with inclusive cache. Alright then, and we also see a lot of varying results. These are algorithm specific. For instance, BFS doesn't result in a lot of improvement, but we see that in the case of SSF, that in the case of SSSP, we see that the latency reduces by around 4 times. So that is a huge improvement. So again, all of this is algorithm dependent, but common theme across all algorithms is that the L1 instruction cache latency will always reduce. And we also have some graphs to support them. So you can look at the graphs and confirm that for some algorithms, the L1 instruction cache latency reduces by a lot, and for some, not by much. Thank you.
So finally, thank you for giving us your time.